Thank you, Norman. Really a pleasure to be here today, and it's been an incredible, amazing journey to be partnered with NVIDIA almost on day one of the company. So, and many more things to come. So today I'm going to be talking about physical AI, which is, as we heard from Jensen on day one, really the next frontier of AI. And in particular, I will touch a lot upon safety as well. And I'm going to show you in details a big breakthrough in safety that we announced publicly last week. And this is the first time I'm really publicly talking about it, so all for you guys. Cool, let's get started. So I think that, by now everybody is familiar with generative AI, right? Which is a very simple idea of, I can actually learn very complex, representations about the world by simply learning to predict what is going to happen next, right? Whether it's text, right, by predicting the next word, whether it's videos, whether it's images, driving behavior, etc. Right? And we've seen that in the digital world has been a tremendous impact. No matter which metric you look at, there is Gen AI everywhere. We all use it when we code. We all use it when we are sending an email. We all use it when we try to summarize maybe trends about our competitors and whatnot, right? So these are tools that have really revolutionized the way that we work with computers. Now, as we think about what has made this revolution possible, there is really three simple key ingredients. The availability of data. We have digitalized the world, the whole internet, together with compute, right? It's not by chance that we are all here at GTC. NVIDIA is, depending on the day, first, second, most value company in the world. This is because they build some amazing technology that has enabled the revolution of AI. And the last bit is algorithms. There is also a lot of research that has happened over the last couple of decades that led into the breakthroughs that have made possible this revolution. Now, as we look at what's happening next, right? The next big frontier is really physical AI. How we can bring this technology to the physical world so that we can have so many advantages for the world that we live in. Right? Whether it's the population is aging, we want robots that are going to help us, whether it is a safer transportation, whether it is fulfillment centers, jobs that we want humans to do better jobs than the ones that they do today. Right? So there is a massive opportunity, multi-trillion-dollar industry, even in just any of the verticals I just mentioned. There is multi-trillions on it. Right? So this is what we've been at Waabi since day one, really very focused is, can we bring the technology that will enable that revolution? Now, when we were looking at, what will be the first vertical where we can deploy this technology that can really scale and can really bring all those benefits, it became very clear that self-driving trucks, in particular long-haul trucking, is the first vertical that is really ripe for this technology. Right, and that's where, with Waabi, we started with that use case, and there is many use cases that you're going to see over the next couple of years. But let's look at, what makes trucking so attractive. Well, first is, just in North America alone, it's $1 trillion market, right? There is not that many opportunities like this, right? So there's a massive economic opportunity for both our customers as well as for ourselves. At the same time, the trucking industry and the transportation industry is really ripe for disruption with technology. In particular, if you look at trucking companies today, carriers, for example, they have a massive driver shortage. Right? And the turnover of their fleets is also massive, 90%. Can you imagine if every year you need to hire 90% of your workforce? Right? That is a massive challenge that they have. And it's one of the reasons that has prevented scaling of fleets of these carriers to have larger fleets. Safety concerns, obviously, most of the accidents that we see on the road are due to human error. So there is a great opportunity for this technology to save many lives. And last but not least is the environmental impact. If you look at logistics today, 20 to 30% of the miles driven, trucks are not driving any cargo. There is no actually goods that go on those trucks. Right? So, and this is because it's a very unoptimized supply chain. So that's a lot of emissions for nothing, right? So with robots, you can actually really, have a much better environmental savings in terms of fuel, but also as we optimize the entire supply chain. All right, so I wanted to bring you also through, the customer lens for a second. which is that why would I care about this technology? Let's say that I am a shipper, your favorite big company with a private fleet. Let's say that I am a carrier. Why do I care about self-driving? Well, safety is something that everybody cares about, right? So that's, obviously this technology, we are going to be superhuman. So that's a big advantage. But there is much more than that. There is also an economic incentive. And let me just walk you through some illustrative comparison here, okay? So a human today, a human-driven truck, on average drives around 80,000 miles per year, okay? And this is because humans have hours of service. If you look at machines, they don't need to rest, right? They can actually drive 18, 20, 22, 24 hours, right? So suddenly you have 3 to 4 times more utilization of every one of the trucks that you have. That is a massive unlock. On top of this, there is additional cost savings, whether it is because of fuel, or whether it is because of insurance, because this technology is going to be safer, or a lot of the ancillary costs that are not necessarily just counted on the wages of the driver that come from having this massive fleet of humans. So if you are, say a carrier or you are a shipper with a private fleet, suddenly there's a massive incentive in terms of the amount of dollars of revenue that you can have for every one of these trucks. Okay, and this is very rough numbers, very simple numbers that I made for you. Right? So it's a massive incentive into utilizing this technology, and this is what we hear from our customers as well as prospective customers: is where can we actually have this technology? Can I buy trucks? All right, so now, hopefully have convinced you that trucking is the thing, right? We have a massive opportunity, win-win for AV players as well as, transportation or trucking companies. Now let's look at where the industry is today. If you look at the industry for self-driving trucks and Class 8 trucks, everybody is going with a AV 1.0 approach. Okay, and the idea of this AV 1.0, for those of you that are not familiar, is that you have a hand-engineered system, which is a massively complicated software stack, where there is AI submodels within that massive system, but you still end up kind of building and hand-engineering the entire thing so that you have to go on the road, drive many, many miles to see what the system cannot do, and then you go and engineer one more module on that spaghetti stack. This is how I call it, right? And this is pretty good. If you look at really the diagrams of the software, it looks pretty similar to your favorite plate of pasta. Okay? So that's it's technology that doesn't scale. It's technology that is very capital intensive, right? Both because you need thousands of engineers, and at the same time you need to crank a lot of miles on the road, right? So we need a better approach than this, right? And in this conference, I don't need to convince you that unleashing the full power of AI is kind of where the industry should be going, right? So let's look at if we want to do this. What do we need to do? Now, going from the digital world to the physical world, there is some additional challenges of things that you need to make sure that you get right, okay? So you actually need to innovate a lot in terms of the technology that you build. On one side, you need a system that is able to generalize. Why do I say this? Is that you're never gonna observe everything that you will see in the real world prior to deploying that system. And as you know, since this is a physical system, and we're talking about a truck with 80,000 pounds, it's very important that no matter what you see in the road, you do the right thing, right? So these abilities of generalization is something that the system inherently needs to be extremely good at. It needs to be good at out of distribution, okay? And this is very different from what you observe today with a lot of the LLMs, etc. And it's not that you can change your prompt and then hope that it will do the right thing, right? This is in real time, safety critical. So generalization is a must. Another topic or important component that you need to do or think about is efficiency. And efficiency comes in two ways. On one side, you have to be very efficient because all the compute needs to run on board the self-driving vehicle. But at the same time, you also need to build a sustainable approach to AI, right? So we shouldn't brute force and require massive data centers and then build nuclear power and whatnot. We should try to build technology that can learn like humans we do, with very few examples, can generalize and do a lot of the things that we need. Okay? So there is this dichotomy of these two levels of efficiency that we need. And the last bit is also very important, which is that it's not enough for the system to be safe. you need to be able to prove it. And you need to be able to prove it before deploying a driverless truck, no human, on the road. And this actually is pretty challenging, as we will see through this presentation today. Okay, so I will walk you through the whole technology, and then at the end, I'm going to talk a lot about safety. All right, so what have we seen is a shift in the industry. Now I talk about the AV industry at large, from AV 1.0 towards what is called AV 2.0. And this is this idea that you're going to have a single AI system that is able to do all the tasks necessary for driving. Okay? And what I call the traditional AV 2.0 is this idea that you can have a black box, big neural network, inspired a lot by BLMs, for example, right? That is able to take the sensor data and then it's going to output all the actions that the system should be doing in real time, right? And this type of approach is learned by imitating what humans do in the real world. Okay, so you have data, footage of humans driving around, and then you try to say, I want my system to do something similar. So this has a couple of problems. One is that it requires lots of data. It requires massive compute needs. So from the efficiency perspective, it's not great. And this is kind of what I'm trying to illustrate here with massive fleets that you're going to need to deploy. At the same time, it's a black box architecture, so it's really, really hard to prove safety here. And if something goes wrong, and then you need to talk, for example, to NTSB or NHTSA, it's very hard to understand what did the system actually did that maneuver? Why did it decide to do something that was actually wrong? So that's problematic in itself, as well as the data needs this technology needs as well, right? And generalization is actually pretty moderate, I will say. So from day one of the company, we thought that type of approach, this was when I started Waabi 4 years ago, was not going to get us there, that we're going to hit a problem with the scaling law. And then we went with a very different type of approach where the idea was we need to inject the ability for the system to reason. And if we actually do this, then we should be able to generalize much better, to be much more efficient, to be much similar to how humans actually do these tasks. And then suddenly we will have the holy grail in order to really build that end-to-end system that can also be deployed across verticals. Okay? So it's a very different type of end-to-end system where the idea is that you're going to force it to interpret what is seen. And these interpretations are actually really, really rich. Don't think of just bounding boxes and things like this. So they're actually pretty high dimensional, but it's able to interpret what is seen, is forcing to reason about what are all the possibilities of the maneuvers that it could do, and is reasoning about the consequences of every one of these actions, and then is choosing the best maneuver given that it understands the consequences, right? It's a very, very different type of approach, and this is actually remarkable in its abilities to generalize, and it's remarkable on its capital efficiency. All right, so just summarizing a little bit, right? So the industry went from 1.0 to traditional 2.0 to the next generation 2.0 with reasoning, where Waabi is the only player that is doing that, okay? And in tracking, everybody is on a 1.0 rebranded, okay? Cool, so it has finally these three capabilities that we were looking for. All right, so I mentioned before that there were three ingredients that actually enable the revolution of digital AI or LLMs, to really take over the digital world. There is actually 4 ingredients that we need for physical AI. Okay, so I talk now about algorithms, right? And I introduce our end-to-end system with reasoning capabilities, right? Let's talk a little bit about data, right? How are we going to train the system? Where does the data come from? So the idea is that, well, you would like to expose the system to many situations, but in particular, you would like to expose or over-index in situations that are critical, safety critical, in situations where accidents are unavoidable, right? To make sure that you minimize the damage, for example, etc. So the real world is not a solution for this, right? You're not going to cause accidents on purpose in order to train the system, right? That's obviously unethical, and that's not something that anybody should do. So we need a different approach, and the approach is going to be simulation, right? Simulation is an environment where you can actually really train and test the system in all these situations in a safe manner, right? But you really need to push the boundaries of simulation to the next level in order to be able to do so, okay? So let's look at Waabi World and our simulator. And actually, all this video footage here is examples of Waabi World, our simulator, okay? All right, so let's get into it. The first thing that is very important, when people talk about simulation, they talk about many, many different things, okay? The simulator that you need to build is a simulator that works in closed loop. What does it mean? Is that think of it as a video game, right? Where you're driving with the autonomy system, the same autonomy system that is going to be driving in the real world, right? But in simulation, and you are basically acting in that virtual world, right? So that you understand and you learn from the consequences of your actions. So it's not static data that you dump somewhere like the internet and then you learn from it. You need to be playing and actioning on that virtual world. Okay, and this is very important because without being a closed loop simulator, you're already lost the battle, right? That's not enough. All right, so let's look at types of closed loop simulators that you can build. One idea that is becoming maybe more and more popular is this idea that, well, I can also use a black box architecture. It could even be the same as my software stack for driving for simulation. And this has, a few challenges, right? Even if you condition and you prompt with text, this is not a controllable simulator. This is also not a simulator that typically you can generate, situations for a very long time. They typically diverge after a few seconds. They look very realistic in the first couple of seconds, and then it's gone. They're also pretty expensive to run, so you're not going to be able to expose your system in closed loop to these situations either. Right? And controllability is extremely important. And on top of this, you want metrics that are automatic and you can trust. You want to understand, is my system compliant? Is my system getting into trouble? Am I driving nicely, etc.? So you need to build a different type of simulator in order to fulfill all these requirements. Okay, and the simulator, is going to look something like this. This is actually Waabi World, okay? But you could build other types of technology. But the idea of Waabi World is that, given a simulation specification, and I will tell you in a second what that means and how you can do this. So given a specific scenario that you wanna drive, it's gonna look very similar to the real world. Okay, so think about as a driving vehicle when it's driving around. What's happening, right? Let's say that I am Waabi driver, I'm the truck, I'm driving around. I'm sensing the environment, whether it's with LiDAR, radar, cameras, microphones, etc. And every time I sense the environment, right, every fraction of a second, I need to perform an action, right? And at the same time, as I'm performing an action, I'm also, everybody around me is behaving, right? It's reacting to me, it's reacting to themselves. And when I decide to perform an action, right, and I tell the truck, okay, I want this steering command, I want this acceleration, etc., then the truck is gonna perform that action. But there is a difference between what it performs and what my motion planning and control says. Any idea why? There is wind, there is friction, there is ice, there is gear changes, there is all those physical properties that you don't necessarily capture in your autonomy stack perfectly, right? So there is some dynamics as well that you need to model. Okay, so this is exactly how we build Waabi World, with GenAI components that actually mimic what happens in the real world. Okay, and so we have multi-agent simulation that is very realistic, right? That mimics how everybody is reacting, and this is not just vehicles, pedestrians, etc. It's anything in the world that you want to simulate. We have super accurate sensor simulation where we simulate in real time multiple cameras, LiDARs, radars, etc. And we also have latency simulation. Why is this important? Because you want to simulate the time it takes to compute on the truck. Because depending on how much it takes, that computation, your reaction time will be different. So your ability to handle situations, safety critical, will be different, right? And we also have dynamic simulation so that you can simulate all those gear changes, friction, wind, and all that, nasty physics of the world, and all within learning components. So that's the way that you can get the beauty of GenAI, you have controllability, and you can get to the next level of performance in terms of the simulator itself. Okay, cool. So we have that controllable simulator, very, very different from what you see, around the industry today in terms of simulation. And let me tell a little bit about how we generate this, what to simulate in the first place. So Waabi World there is an heterogeneous way to actually create those scenarios. And it's built so that depending on the use case of how you're using simulation, there will be certain things that you want to do. Okay? And we use Waabi World for everything in the company. Just think about it. So sometimes engineers, safety engineers, they want to really have precise tests. This is, for example, where they create requirement for VMB, which is very important as well for the safety of the system. Right? Then the user can actually prompt and then create very specific situations. And you can decide the level of specification, and the rest will be completed by the simulator. At the same time, we have this really great ability to any single mile, everything that we have ever driven, to clone automatically and create simulations with it. And we can create variations of those simulations. And I will show you in a second some examples. This is a massive unlock if you can go from a log that you recorded in the real world to simulation, and you can create what would have happened if, right? This is the kind of questions that we always try to answer. You can also run this in a full generative mode so that you can just control the distribution from which is sampled, for example, right? Or you can have what we call adversarial optimization. And this is the idea that we want a very efficient way to capture or to understand where our software Waabi driver has potential issues, right? So the simulator then is going to play adversary, and it plays this two-player game with the software stack where it's creating simulations that with high probability we will fail, right? And that's the way that you don't need to run billions of simulations every time that you do tests or regression tests, for example. Okay, so it's a very, very comprehensive set of ways, and you can actually combine all these things together. So let's look at some examples. And this is supposed to have some audio. I don't know, you guys can put that. Otherwise, I will just talk. Cool. So what you see here is that on the left is real world, and on the right is simulation. So what you can do is we clone everything in a way that is controllable, right? And then you can start playing around. You can remove things, you can add things, you can change the time of the day, the weather conditions, you can change the platform that is actually driving from something that is a passenger car to a truck to any form factor, all automatically by simply cloning the world and creating permutations, variations of this world, right? And that's the way that you get, you're grounded in reality, right? And at the same time, you create many things that you have never observed. Okay? You can drop, vehicles and things that you capture somewhere else in the world to create new situations somewhere else. All right, cool. So we can create these variations. Now I'm going to show you Waabi World in closed loop. I don't think we have ever shown this actually in public, so I guess this is the first time. So on the left-hand side, every pixel, every laser point, everything is simulated. The behavior of the actors, etc. Okay? So in every one of these videos, everything will be simulation. But we are driving with the entire autonomy stack in that simulated world. Okay? And what you see here is that we're going to take a situation that we have cloned from the real world. In this case, we're just driving down the highway. This is somewhere between Dallas to Houston. And then basically there is a situation typically where you have a big rig next to you and some traffic and whatnot. Okay? And now we're going to create different variations. And what you observe here is so it's our self-driving truck. You have, some of the interpretations of what it's seen, and sort of the maneuver that it decides to do. Okay. So in the right-hand side, what you see is we have changed the situation where now we're going to take one of the actors that's going to do a pretty aggressive cut-in in front of us. Okay. So now we're going to need to reduce the speed in order to encounter or react to that situation so that we don't crash into that vehicle in front of us, right? And you can vary how aggressive you do this, right? Then we can decide to, now let's modify actually the two actors. Now they are both going to cut aggressive in front of us. I'm just illustrating, some of the things that you can do here. And you see here with, it's super realistic, and in terms of the software, it's really, the same in real time in the simulation as well as in the real world. Okay, and you can do this very, very efficiently, so that you can do, all these different tests, permutations, etc. You can run all these permutations, on the cloud, and this is just a very simple example with two players, right, or two reactive actors, but you can inject whatever you want on any of these situations. And it's the OD where we drive, right? This is actually fascinating. So we can, as I mentioned before, we can generate things from scratch. So we create our own high-definition maps for safety, level 4, extremely important to create high-definition maps. This has been, a kind of something that people have criticized the use of high-definition maps, particularly level 2 players. But for safety, they're amazing. With trucks, we need to see super far. Okay, so this kind of enhanced safety, right? We think of them as an additional sensor. We also do online mapping and everything, on the vehicle as we drive. But we can create them like actually super cheaply. It costs us less than $50 per mile to create a map. Right, so it's super scalable, right? So maps are actually scalable, it turns out, if you have the right technology with GenAI. All right, so we can now generate, tell the generator to generate initial conditions, and then from there, you tell the actors to then behave. And then you can play with all these modes, different types of actors, etc. So whether it is, you control them to be very precise, you generate, or you create them to be adversarial, etc. Right? So the generator can actually play and create all these things in all these variations and all this stuff. Right, and in a way that is very, very realistic and really mimics whatever distribution you want to sample from, right? Whether it's safety critical, whether it is the real world, etc. So it's a very comprehensive simulator. And the other thing that is very important is that you shouldn't just have one actor model. You should have many actor models, many ways to do this, so that when you're testing and training the system, you don't overfit to a particular type of actor. Right? Because don't forget that humans behave in many different ways, and you want to make sure that you capture all this, and then you react accordingly. So it's a very, very comprehensive simulator, really, really powerful. All right, so now we're talking about physical AI. We need one more piece, right? The robot, very important. All right, so let's talk 2 seconds about the robot. And so this is an example of one of our self-driving trucks. And what is important is that as you are developing this technology, when you're starting, you can retrofit these trucks to create redundancies. But in order to build a path to scale, you can't just retrofit, right? This is not safe. This is not scalable. So a vertical integration into an OEM platform that is redundant from the factory line, where you can really integrate your sensors, your compute, and your software at the factory line, is tremendously important. This is, we believe, the only path to really scale. A couple of weeks ago, we announced our go-to-market partnership with Volvo for the joint development and deployment of this technology within their new Volvo VNL Autonomous, which is this redundant platform that is really, really exciting and really a leader in safety. Okay, so now we have a path to really, scale our product. So that's very, very exciting. And then let's this compute. And this will not surprise anybody, right? Which is, NVIDIA has been our partner, both, we do a lot of things as it relates to the cloud, but also for the compute on board. Drive Thor is very, very exciting. Okay, cool. So we've been working very, very closely with the team. All right. So in the remainder of the talk, I'm going to be talking about safety. Okay, and this is paramount as we are gearing towards deployment driverless with no human on board. Safety is not something that should be an afterthought. Safety is something that you need to think extremely careful about your approach. So let me talk first about what does it mean safety? What do you want your self-driving vehicle to do? And it's not just about being better than a human. It turns out there is a couple of more things that you would like it to do. Well, first is that you would like it to have less risk of collisions than if it was a human-driven truck. I think that's very easy for everybody to agree upon. Also, it's important that you drive responsibly. What does it mean is that not only you should avoid collisions, but you should avoid getting into situations that are close to collision, right? So you need to be very safe. You should also improve not just safety for you and count your own collisions, but safety for all. If you are behaving in a way that is, is very unpredictable, even if you avoid the collision, you might cause somebody else to have a collision, right? And that's a problem. Minimal disruption to traffic, right? To traffic flow. For example, if they are emergency responders, it's very important that they can actually continue to do their job and you're not blocking traffic or anything like this. There is going to be many changing conditions, whether it's going to be bad weather, fog, etc., and you need to make sure that you always drive responsibly. I told, at the beginning, I mentioned generalization, right? So you need to be able to respond to the unknown because there might be things on the road, a couch in front of you suddenly, which we saw actually in the real world, that you still need to be able to drive safely. And the last bit is compliance, right? You should be compliant with the law, right? You shouldn't be driving on the wrong side of the road. You should be, following traffic rules like traffic lights and things like this. But I want to make sure that this is very clear, which is, some of our competitors have said that compliance comes first, and then it's all these other things, or a subset of these things, right? In their case. And I will argue that this is a bad idea and this is not safe. It's very important that the first thing that comes is safety. And if you need to be uncompliant to save a life, you should absolutely do that. Let me show you an example. This is our trucks. All right? So if this place, we are driving around the highway, it's busy on the left side, suddenly somebody stops in line. If you are not uncompliant and go to the shoulder, you potentially are going to kill somebody, right? So it's extremely important that compliance doesn't come first. It's extremely important that safety comes first, okay? We couldn't lane change because there's somebody occupying our lane, okay? So hopefully this, is a clear motivator of why safety should come first, right? Imagine if you are on this highway right next to our self-driving truck. All right, so how do we prove safety? So let's get into this is all great. We know what the self-driving vehicles should do, but now we need to prove it, right? Being safe is not enough. You need to be able to present a scientific safety case, not just a checklist of, we are safe and just trust us. It's like, here is the evidence of why you should trust me. All right, so it turns out that highways are notoriously difficult for safety case. Right? And why is it the case? Well, let's look at the statistics. This is for human-driven trucks, okay? Let's look at the statistics of when bad events happen. Property damage happens every 100,000 to 150,000 miles, okay? So it takes 2 trucks typically for a whole year to actually see one of these events. A small body injury, typically every 1 million miles, okay? These are round numbers. Life-threatening, every 10 million miles. Fatalities every 10 million miles, right? So think about, if I want to have a statistically significant safety case, how many of these events do I need to see? If a human can only drive 80,000 miles per year, right? What's the size of my fleet in order to be able to see statistically significant evidence that I'm safer than a human? It doesn't work, right? So we need something else, and it's very clear that, well, simulation is the only solution that you have. Now, when we talk about simulation, again, it's about closed-loop simulator. If your simulator is just creating static data, who cares? You're not actually testing the system, right? So we need to really create a simulator that can replace all those miles that we cannot do because nobody has the fleets, and you don't want to create accidents on purpose, right? All right, so I think it's important that to think about, there is plenty of simulators out there, and everybody has typically multiple tools instead of like Waabi World, a single tool. But there is like different levels of those simulators. And the majority, if not all of the simulators of the industry are in this first category. And this first category is what I call standard simulators, which regardless of the technology that they employ, what they can do is that they basically support software testing. Can catch bugs, can catch big regressions that you have from one release to the next release, etc. Advanced simulators are kind of like the next big category. And this is the idea that not only your simulator can actually tell you about how well you are doing, but can identify the specific situations where you're going to have trouble. Right? This is very, very important. Imagine if we know that we have trouble with a particular type of situation. We can instruct our safety drivers, and we can also build better technology in those cases. Right? And the holy grail is what I've been talking about for safety, which is, can we actually have a simulator that is the same as the real world so that we can actually use it to prove the safety case? And then since I can run this on the cloud, I can actually break the statistics that we saw before. Right? I can have a much more scientific safety case. All right, so now if you want to use simulation, then you have one more question to answer, which is, well, using simulation, is great, but it doesn't matter unless you can prove me that it's realistic, right? If your test is going to say something else, who cares how many tests you drive? Whether it's billions, trillions, like whatever, right? It's unrelated to the real world. So let's look at how can we measure realism. And I will argue today that the important thing of measuring realism is not about how cool my videos were today, right? Okay, it looks very realistic to the naked eye, but that is not important. What is important is that when we take the entire software stack and we test it on simulation, under the exact same situation, it does the same as in the real world. So the outcome, the trajectories, the behaviors, the heartbreaks, whatever it is, should be the same on both situations, okay? So that's where we want to measure on the outcomes. So let's look at what we've seen in terms of measuring realism. And there is nothing in the industry, really. So I'm going to refer to academia, and then I'm going to show you how you can really prove realism. All right, so in academia, what you see is that you capture, you have your simulator, and you have real-world data, and then you are going to look at the difference between the distributions of what you see in simulation and what you see in the real world. Right, so use distributional metrics, for example, heartbreaks. And then you say, is the distribution of heartbreaks similar in sim versus in the real world, right? Now, this is a step forward, but this is actually still very primitive because where those heartbreaks were could be in very different situations. So I'm still in the standard level of simulation. I'm not proving anything, right? Because I don't have a one-to-one matching, okay? So arguably what you need is the per setting where you have real-world data, you can create the same simulations, and then you can measure realism. And we're going to measure this realism at the level of the outcome. What does this mean? Is that we want to compare what we did in the real world to what we did in simulation. We take the trajectories, and we're going to measure the difference. And the opposite of the difference is going to be the realism score. This is exactly the ultimate goal, right? You want to drive exactly the same thing, the same way in simulation versus the real world. Now, we want to do this in a per setting. So how do we get these per scenarios? Well, we can refer to creating these digital twins, right? If we can create these twins, then suddenly we have exactly the same thing in the real world as in simulation. And we can use these digital twins to seed the simulation. We are not just replaying, but we are initializing the simulator in exactly the same place, with the same actors, with the same weather conditions, etc. And this is very, very powerful, right? So we create a twin for every one of those situations, every single mile that you have ever driven, and then you're going to run the simulator and compare the outcomes, okay? And in this case, we're going to run controllable simulation, and it's Waabi World, okay? Cool, so it turns out that if you do this measure with Waabi World, the realism score is 99.7. It's amazing. What does it mean is that basically driving in simulation and in the real world is the same thing. And let me just prove you with a few videos, okay? And what you're going to see here is also Waabi driver behaving in the real world and in simulation, okay? So in purple, you see kind of the trajectory of what it's intended to do, right? And you see also some of the interpretable representations as it goes, okay? So what we see here is that, and every LiDAR point, every single camera pixel, everything is simulated, and it's closed loop. Every single actor is a reactive, intelligent GenAI actor. Okay, and you see that in this particular case is one of the things that is difficult with trucks, which is that you need to change lanes when you have an actor on shoulder, right? So the idea is, are you detecting in the same place? Are you actually doing the safe, a similar maneuver, etc.? And as you see here, is very, very similar. You can look at things like merges, which are actually pretty hard as well. Are you, for example, here slowing down to enable folks that are trying to incorporate in front of us and giving the right gap? And as you see here, same thing in simulation versus the real world. It's mind-blowing. Like, you cannot see the difference. And not just on the pixels, but on the outcome of what the entire software is doing. It's the same release driving on simulation versus in the real world. Okay, and you can say, you can do similar things here for, other situations, etc. Okay, cool. Let me just speed up. All right, cool. So other things is that, well, the outcome is the important one metric, but we actually compute all sorts of metrics, right? And because it's a controllable simulator, we can look at the realism of every model, the realism of whatever system under test, if it's a traditional method, every one of your components, different models, different ways of computing realism of the system level metrics, etc. And all automatically at the scale for every model you have ever driven. Amazing, right? So now you have a framework where you can really prove realism. And the last bit I want to say is that, so these digital clones and pair setting is to prove realism. That doesn't mean that the simulator does only that, right? This is the framework for proving realism. Now the simulator does coverage-based testing, generates new scenarios fully from scratch and all that stuff, right? And we do it in a way that is very, very efficient. Like instead of just sampling your ODD at random with, kind of like homogeneous, like everybody will do, is that we do it in an intelligent manner where you look at, close to the pass-fail boundary, for example, you sample much more efficiently. And this is the way that you can do coverage analysis for your safety case super efficiently. All right. So now we have, finally a software stack, Waabi driver that is able to generalize, it's efficient, and it's provably safe. Now we can actually really prove it, right? And thanks to Waabi World, our simulator, we are able to do so. So I'm going to stop here. What you're going to see is, by the end of the year, you will see our self-driving trucks driving autonomously with no human on board. And I share with you today a lot of the underlying technology underpinning the ability to get there much safer, much faster, with a much more scalable approach, much more capital efficient as well. Thank you.